Okay, welcome back everyone. So this video is designed to be watched after you've seen the basic graphical analysis video. So the idea is that you know how to take data and turn it into a somewhat straight line form. So here's an example. In our Zany-Zircon-Zinger's lab, we've plotted distance versus time squared. And what we want to do is we want to write an equation. Instead of writing an equation of the form y equals mx plus b, we want to write an equation of the form d equals slope times time squared plus intercept. So the slope and the intercept are both things that we need to derive from the graph. Okay? And again, on the y-axis we have distance playing the role of y, and on the x-axis, like we talked about previously, we have time squared playing the role of x. Okay, so what I'm going to do is attempt to draw a line through my points. Now, you're not going to have uncertainties on your second graph, and we'll talk about why that is later on. But you can imagine on another graph for another lab, you might have uncertainties. Okay? What you want your line to do, and it shouldn't have any arrows, is you want to try to get the best straight line fit you can that tries to hit all of the uncertainty bars. Okay? So this is one example. Now, there's going to be others that you could choose, but this one works for now. Alright, once you have this, pick two places where this line seems to intersect the grid. And you'll notice that I have a much finer grid on this. Okay, so we are going to calculate the slope using these 2 points. And it looks like we have a distance, and this is why it's important to have a nice simple scale. That looks like 47.5, and down here it looks like 7.5, so we have a rise of 40 centimeters. Okay, right here this looks like 0.48, and down here this looks like 0.04. Hopefully you can see that every tick mark represents 0.02 on that axis. So this is 0.44 seconds squared. Notice that I have to use the same unit as I have on the axis. Okay? So this means that the actual slope is going to be the rise, which is 40 centimeters, divided by the run, which is 0.44 seconds squared. So I grab a calculator, and that means I have a slope of about 91, and my units are centimeters per second squared. Okay, so that's the first part. Make sure you pause and rewind if you have any questions at this point. Now for the second part, we need to determine the intercept. And I can look at the graph, and that right there, well, let's see, it's between 2.5 and 5. If I had to guess, I would call that maybe 3.8. Okay? So the intercept is equal to 3.8 centimeters. Notice that I use the unit on the y-axis. Okay, so now we're ready to try to write this equation. And so remember, we're trying to fit everything into here. D equals slope times t squared plus the intercept. Alright, so just as a reminder, we want D equals slope times t squared plus the intercept. Okay, so we plug this in. The slope as we said, is 91 centimeters per second squared times t squared. And the intercept is 3.8 centimeters. Okay, so this equation here is the mathematical law that relates distance to time. Mathematical law for distance versus time. Okay, you could say something like the relationship between distance and time for a marble rolling down a ramp is d equals 91 centimeters per second squared times t squared plus 3.8 centimeters. Okay, now let's do a quick dimensional analysis. Is this a possibly correct equation? So distance, we're going to go with centimeters. We're given that we already have centimeters per second squared. Time is going to be in seconds, and we can square that because we have to. And then we have centimeters. So is everything in centimeters? Looks like we have centimeters here because the seconds will cancel, and centimeters here. Okay, so this equation is dimensionally accurate, and that's how we know that it quite possibly is the correct law for distance versus time. And as a matter of fact, if you plug in a particular time, you should get a point that exists on this line. For example, look at this point right here that I've just sort of focused on. This point is somewhere around 0.29 seconds squared and something like 30 centimeters. Okay, so if we just check this, I'm going to scroll, whoops, where do we have some space over here? Okay, so is 30 centimeters equal to 91 times 0.29, because that's what t squared is. It's 0.29 seconds squared plus 3.8. So 91 times 0.29 plus 3.8, and that's 30.2, so I'd say that's close enough. Okay, so this is the basics behind how to analyze a linear graph. And what we want to do for pretty much every lab is try to get our data in this form, y equals mx plus b, and then find the slope and intercept.